So welcome to the second video of the first lesson, and today in this video we will be talking about Markov decision processes. To give you a little outline about the next 6 lessons and where we go through this, you can consider the following graph. So in this lecture we will talk about Markov decision processes, which is basically the formal framework that we define our problem. And in the upcoming videos we will build upon each previous video to actually solve such a Markov decision process, which basically means that we learn how to actually act in the environment to optimize and to squeeze everything out of our Markov decision process to actually optimize the cumulative reward we get from the environment. Okay, before we actually start defining the Markov decision process, we just go back to something that you know from the last video. So a Markov decision process is our tool to formulate our reinforcement learning problems and to define them. And the Markov decision process is basically defined as a 5-tuple. A Markov decision process depends on or contains a set of states that we are actually used to describe the states we might end up in. We see example for this in the upcoming slides. We can take a set of actions. We have probabilities that are assigned to certain state transactions. So that actually take us from one state to another. We have a reward function that defines how the environment provides rewards to us, and we have a decay factor that actually weighs immediate reward over long-term reward. And to come back to this figure in here, the age environment interface, at each time step, the agent is at a certain time step st, and it performs a certain action at, and it receives a reward rt from the environment. On the other side, at each step t, the environment receives an action at from the agent, and it provides a reward rt to the agent. Internally, it moves from a certain state st to a certain state st plus 1, and it increments a time counter. So we have a discrete time step that is incremented every time that we actually perform a state an action in the environment. 2 things to know from this point. There's actually 2 different problems we consider in this class. It's either episodic reinforcement learning problems or continual reinforcement learning problems. In the episodic cases, the environment stops at a certain point in time. So we call this episodes, and which actually terminates the interaction between the agent and the environment. Like in a game, the game is over. Or on the other side, we also have continual problems, like we see this like balancing a grid, a smart grid, or having a production line that is used to run forever. And the second note at this point is that if you read up the literature, or if you go through and you Google around it, you will see conceptual differences between the notion around the state. So in this case, the environment provides a state st to the agent, and there is conceptual difference if it only provides an observation of a state to the environment or not. This basically means if you consider like you're having a robot, and your robot has a camera on it, and you see the image or the camera image of the robot, and the question is if this image completely describes the environment at this point in time. Probably not, because it's just one view on the environment. But this can actually be solved by other things, and at this point there is a conceptual difference, but we can omit this for simplification easily at this point. Okay, so actually to formulate and to explain what a Markov decision process is, let us just look into the certain components of of an MDP. Okay, so the simplest assumption or the simplest basics of a MDP is a Markov process. So we might also know Markov processes from related concepts, like from hidden Markov models. And here what you just define is you have your set of states that you could actually be in, which could in this simple case just be your daily routine. You're either at home, or you are sitting at the computer, or you're drinking a coffee, or you're chatting with a friend. And there is like the states is defined by the nodes, and you can transit between different nodes through edges. So the nodes are somehow connected. Not all of them might be connected. So to go from home to chat, you need to first go to the computer or to the coffee to actually go into chat mode. So you have actually nodes which are representing your states, and the edges represent transitions between those states. So in this case, if you have a Markov process at this point, what you usually do is you just define probabilities that describe how likely it is to transit from one state to another. For instance, if you are at the computer and the probability if you are at the computer and you are then you're then going to chatting mode with a friend is maybe a chance of 10%. You can easily put that on the edge in here, which basically says from here to there, the chance is 10%. And the way you usually encode such information is you use a table or a matrix, which is basically organized like this. You have the computer, which is the state you're currently in, and you want to go to chat, and the probability of going from computer to chat is then a chance of 10%. Yes. Okay. And what you also see is you cannot directly reach from home to chat, which is encoded with a 0 in here. So actually there is no direct way of going from home to chat. And what you can then do is you can just calculate the probability of going from home to chat over all the paths, and you can there's algorithms to actually solve this that you can use to actually derive such a probability. Okay, so if you have something like this, this is the two main components of a Markov process, of an MDP. We could just add rewards. So we have seen that rewards are a central concept that we also use in reinforcement learning, which we also optimize for, and we need to somehow introduce this to our Markov process. And if we just do this is called a Markov reward process. So a Markov reward process is basically a Markov process added with a reward function on top. So in the simplest case, what you can just do is you still have your probabilities that let you transit from one state to another. I just removed the table at this point, but the probabilities are still on the graph. But what you now do is you add rewards on top of the edges. So actually in here, if we are at home and you go from home to coffee, which is actually a 40% chance, you may receive a reward of 1. And this is something that you encoded. And if you do this, you can also use a table or a matrix to actually represent this. So in this case, if you go from home to the coffee machine, you get a reward of 1. And if you have a self-transition from home to home, you also get a reward of 1. You also might get a negative reward, for instance. So if you're supposed to work at the computer and you go to the chat mode, you get a reward of -3. And this is always also encoded in here. Okay, so far we have a Markov process. The Markov process lets us define certain states and probabilities between for the transitioning between those states. And we have a reward that we also may attribute to it, so we can also define how good it is to transit between states. We did not yet introduce any decision variables, so everything was just going, and we couldn't actually take actions to influence any behavior or any movement between states. And this is what we then introduce to our state description, and this actually then transforms the Markov reward process to a Markov decision process already. So in this case, imagine we have the grid world example. I promised you that you also see this a lot. And we might also, we have a state space. A state space might be encoding the X and Y position of the robot. And the reward is, for instance, encoding in here. So 0 may be everywhere, and +1 in here, and -1 in here. Episode terminates when we are receiving these rewards. And we define our actions to just be going up, going left, and going right. So the action state is really just a set of actions that we might take. However, now what we still need to do is we need to somehow define or combine this with our state transition model. So the probabilities to actually transit between two nodes. And now this also depends on the action we take. To actually formally and fully cover this, we need to rely on a state transition model. So actually, if you look back in the real world, there is a true state transition function. So if you are in a state st and you want to go to a state st plus 1, so the state st plus 1 depends on the state st where you are in and the action that you take. And the thing is, if you maybe want to reach, for instance, this point in here in the grid world, this could either be reached, of course, if you go from here and go up, or if you go from down. These are the obvious cases. But there might also be dynamics introduced by the environment that actually have an influence on the actions that you take. So if you, for instance, consider that you're moving on a frozen lake, and in this case, you can easily imagine that taking a certain action does not necessarily take you one step forward. So there's also dynamics in the environments that actually lead to the fact that a certain action derives a different next state that you would expect. So there's probabilities assigned to a state and an action where you actually end up into. And the next thing would be like if you have, in this case, for instance, the grid world, and you maybe this is a pillar, so something really big, and there is wind in here. And for instance, if you are in here and there's a strong wind from the left side and you go up, this might blow you into the -1. So this is something that you describe with a state transition model. So basically meaning that there is a true state transition function that is encoded in the environment, which might be very complex. And this state transition function is defining the next state as t plus 1 where we end up in as a probability for which the input is st and your action at. So in this case, what you usually do is that you say, okay, if you move up, there's a 80% chance that you really move up, and there is a 10% chance that you go left and a 10% chance that you go right. And how to really encode this is actually you encode a state action probability function p in here, which is actually a cube, which says for a source state in here and a certain action, that is a certain probability that you end up in a target state. Of course, this sums up to 1 and this sums up to 1. So this is actually how we encode things in our environment, and you will see this and you will implement this also in the exercises. Yes, so actually, depending on how you implement it, you could implement for each action A1 that you can actually take, AY, you have a state transition matrix that defines if you take in this certain state, this certain action, you end up in here, for instance, with the probability pi. And this could be encoded like in a probability transition matrix per action. Okay, so this is our Markov decision process. We will talk about one missing factor in the next thing, but let's talk maybe a little bit more about our state st that I also introduced a little bit the problem with partially observable Markov decision processes and fully observable Markov decision processes. So in principle, if you define a sequential problem, the state that you're actually in is fully defined by the history of the sequence of all the observations and actions and rewards you get over time start from the beginning. So if the beginning is always the same, your state is fully defined by the whole action state reward sequence that you got. And from this definition, you can actually define 3 different definitions that actually can let you define st. So actually, if you're implementing the environment, what you could usually do is you can say to the environment, to the agent, you can say, okay, I give you the whole state of the environment. So in the example with a robot that is moving around in a corridor, which the observation would be just the camera image, I will provide everything. I will provide the pressure in the rooms, or also the information of other rooms. So that would be the full environmental state. That is usually something that's private to the environment. It's not visible to the agent, and it also contains a lot of irrelevant information. And then if we use this as a state, we can just use HT, which is just a concatenation of all that, to pick the observation and reward from the environment. Or we can define it as the agent state, which is something that's actually used in practice. This is something that is private to the agent. It's just the history of observations, rewards, and actions. And what we usually do, we define, so this is what the agent gets, and we define our state representation that we use for our Markov decision process through some function over the history. So this is what we get from our environment interface, and what we actually use to define our state is some function over this, which actually could be just the concatenation of this. But actually, this is not really practical in practice, because it tends to be very huge in practice. So what we actually want to use in practice is the information state, which we will define on the next slide, which is basically the same as this one, as the agent state. So actually what the agent can observe from the environment with some special constraints on it. So it's like a function with constraints on it, which we will define on the next slide. This leads us actually to the Markov property. So we talked about Markov processes and Markov reward processes, but where does the Markov come from? That's the actual question. And the basic assumption of the Markov property is that a state ST is Markovian if and only if it satisfies the following property. So the probability of ending up in the state ST plus 1 is, of course, depending on every state that we had in the beginning before. And if we have a representation that says, okay, this is equal to this, then the state representation satisfies the Markov probability. This sounds a little bit weird, but what does it actually say? This actually says that all the past states that we were in the beginning, so like from 2 time steps away to the beginning of the episode, we were in some states. And actually, what we want to say is that the outcome where we end up in, it's not really depending on the early states that we were in, but only depending on the current state. Which basically means that we need, or that we want to find an encoding that says that the current state ST captures all the relevant information from the history, and this is encoded in this step. And this is the assumption, the basic assumption of the Markov property that we need to actually define a Markov decision process and to solve it. There's a nice sentence that also captures this, saying that the future is independent of the past given the present. So if we know a certain state, so a certain history leads us to a certain state ST, and everything that happens from here is just depending on this current state. It is completely irrelevant where we have been before. And here's also maybe now more intuition about why I differentiated between fully observable and partially observable. So there is like, if we have a direct observation of the state, then we can just say, okay, the observation is the state information that we get. So we have a fully observable state, so we get the Markov state from the environment. But there's also cases where the state or the information that we get from the environment is not defined in a Markov state. Then we talk about a partially observable Markov decision process. And in these cases, we need to pre-process the observations and states to actually get a Markovian representation of this. Yes, okay. So in practice, how can we construct or ensure that such a Markov state? How can we actually assure that the Markov property is satisfied in practice? So, for instance, imagine that we have a car and we want to we want to have a lane. We want to keep a lane. We want to have the car keeping a lane, and we could and at some point you define your MDP and you want to know, okay, how do I define my state? So is my state defined by the position of the car on the road? And probably maybe that's not enough. So maybe or put it a different way, you get the following measurements from the environment. You get the speed of the angle, and the speed and the angle of the car, for instance, which could be something that you might wanna say is enough for to actually keep the lane. But the problem is that actually to come up with a current action to actually keeping the lane, this information is not capturing everything. So you do not know actually the lateral acceleration. So if you're breaking out of the lane, this is something that is not encoded by just having the speed and the angle of the car. And also it's not clear, and you also have no idea of the angular velocity at this point. So you have to deal with this. Actually, what you need to do is that you need to augment your state to actually have this components also in your state representation. You can do this either by computing it or by just keeping track of past states and to combine them to a state representation that allows you to actually control, to get a representative state of the car at this point. Another point or another example, for instance, to make it more clear is, for example, the grid world. In the grid world example, you want to define your MDP, and the question is, how would you define your MDP in this setting? So in this case, you would just have states defined by x and y coordinates of the robots. In this case, they might want to be discrete. So it could be 0 to 3 in the x direction and 0 to 2 in the y direction. And you define certain actions going left, right, up, down. So this is something you will also do in the exercises. But there's also for instance, bigger state spaces or continuous state spaces. In this example, for instance, it's also well known hello world example in reinforcement learning. It's cart pole, and the basic task in cart pole is to balance a pole. So you have a small cart at the ground, and you have a pole, and you want to stabilize it that it doesn't fall over. And to actually describe such a Markov state for a cart pole, it's not enough to just say where is my cart currently and what's the angle of the pole. What you also need is you need to know the velocity of the cart. So actually, if you say push the cart a little bit to the left, it depends on is the cart already pushing to the left. So you actually put a force on the cart, but it's depending on the current velocity, how you would end up in. And another thing is also, if you just have a picture of the pole, you do not know the angular velocity. So actually what you do not see through a single picture or a single angle is if the pole is already tipping to the right. So if it's already tipping to the right, you do not need to actually enforce it tipping a lot more to the right. You maybe push it a little bit so that it's not tipping so far. And this is the angular velocity, and the angular velocity in the above setting. And then you define, for instance, just the actions going left or going right. And if you have this representation of states and actions, and of course of your probability transitions or your dynamics of the systems, you can actually come up with a controller that stabilizes the pole in here. Okay, another example is, for instance, Tetris, maybe also representative for the Atari examples that we also had last lesson. Episodic is a nice example for an episodic task. So you run in episodes, and at some point it's over, either because you crashed the high score or because you die, because you have reached the top. And you have discrete actions, so you can go left, right, you can rotate, and you can go down. You cannot push it up. It's an episodic task, and you have discrete actions. And the question is, how do you define your state space? You see it is very complicated. You could say you can say, for instance, you define it by a grid and is it occupied or not, which would be a valid state space, but it's huge. What you will see in practice at later points is how you could actually use convolutional neural networks to extract a Markov state from these images and then use it to actually derive actions and train that end to end. But what you would do is actually you would need to come up with some state representation of this environment observation to actually optimize anything in the environment. Okay, another really nice example, as you also saw this last week. There was a NeurIPS competition 2 years ago where you actually had the task to define an agent or to train an agent that actually uses a prosthetic leg to run through some world. So in this case, really, so you have muscles that you really activate, and you have degrees of freedom where actually every joint angle can be adjusted, and you get a reward signal which is basically a negative distance from a requested velocity. And the actions in these cases are really like stimulating the certain muscles at this point. Okay, now you saw the examples for certain Markov decision processes, and we saw certain examples where we had states, actions, probability, transition matrices, and rewards. However, there is one thing still left to discuss, and this is the discount factor gamma in here. To motivate this a little bit, recall the fact that we had in the beginning that the actions that we take have consequences, meaning that an action that we take at a certain point in time yields a different reward sequence than if we would have taken another question. And the question is, look maybe at the following example in here. You define an MDP and you want to have a robot that goes through a grid world, and you have and you can actually go to different end positions in here. And the question is now, if you have two sequences that you can go through the world, and on the one sequence in here, you get, at each point, you get a diamond as a reward of +1 for instance, or you can take the other sequence on the right side in here and you get a +4, but only at the end of the episode. And the question is now, in such situations, which sequence would you know, or which sequence should we prefer? And the question in order to actually in order to formulate this is to add a discount factor that allows us to decay the value of rewards that we get in the future over rewards that we get now. Okay, but actually let's make this a little bit more formal. So the basic thing why we define the MDP is because we want to have a mathematical framework that allows us to maximize future rewards. And in practice, what we actually see is, if we calculate, so given our MDP and our states and actions, we get each of our sequences that we go from a certain starting position to an end position. We see sequences of such a form. So actually, we start in an initial state, we take an action, we receive a reward, we start in an action tape, we get into a next state, we take another action, we get another reward, and we do this over and over again and end at some point as t. And the question is now, what happens if our problem actually never stops? So if t goes to infinity, which is, for example, in the data center cooling example or in the card pole example and things like this. And the thing is, what we actually want to have is, we want to define for such an episode that we take, so our robot goes through the environment, and the question is, how good is the robot when it goes through the environment? And actually, what you would immediately say is that, okay, the ultimate reward, or the ultimate this episode actually, the episode is as good as, so this sample is as good as all the rewards we collected along the way, which basically lets us define the total discounted reward, so discounted by gamma reward, or also called the return of a single episode, so of a single example, which can be simply defined by the sum over all the rewards that we have got until the end. The end could be infinity, or the end could be some terminal state. And if we add the gamma factor, actually letting us decay future rewards, so we say, okay, the rewards we receive in subsequent steps are less worth than the rewards we immediately get at this point. So what we just need to do is we need to decay the future reward by gamma and by gamma squared and so on, letting us define the total discounted reward of the episode by this one. So the sum of all the rewards we see until the end, and we discount them by our gamma factor gamma to the power of the times that we receive this respective reward. Setting this gamma to 0 leads to a very myopic evaluation, meaning that we are only interested in immediate rewards, and setting gamma to something like to 1 says that I don't care if I get the reward immediately or if I get the reward in 1,000 years, it's equally likely to take this. And actually, what's really convenient is that this infinite sum gets finite if we use a gamma less than 1. So actually the question now is, why should we actually in practice discount the rewards by gamma? The case is, as I also maybe talked a little bit about it in the last sentence, it's mathematically very convenient to discount the rewards. Because as you said, if you have very, very long reward sequences or episode sequence, if your episode is very, very long and you have a lot of rewards along the way, so actually if your time steps grow to infinity, it's not very good to actually approximate a sum that goes to infinity. So it's mathematically very convenient to discount the rewards, because at some point rewards get very, very, very small and you can actually approximate the value much, much more early. The next thing is it avoids infinite returns in non-episodic problems. So actually if you have a problem that runs forever and you get a +1 reward every time step, your sum will grow to infinity as well. So your return will go to infinity as well. And also another case, which is maybe not slightly that intuitive right now, but it's very, very important, is that that we use model assumptions, that we have a probability transition matrix implemented in our MDP or in our environment, and usually this is just an approximation of something that's really the case. And if we use a gamma factor that is lower than 1, helps us to alleviate a little bit the uncertainty that our model is prone to. So as our model is not perfect, it is good to decay future rewards, because with future time steps our model is more inaccurate. The question is, can we use a gamma of 1? Sure. In principle, you can, so the math is completely fine if you do this. So if you have an episodic setting, this is no problem. Or if you definitely know that there's a terminal state that absorbs everything. Should you use a gamma of 1? No, in practice you shouldn't do this due to a number of reasons. But you should, or you can easily take values close to 1. So in practice, the default configuration of many algorithms is something like 0.995 or 0.999. Okay. Now having all that elements in our MDP and having the discount factor, now the thing is, how does it help? How does it help us to actually solve the MDP? So actually we always talked about solving an MDP, and what does solving an MDP actually mean? So what we are interested in is actually to get a good understanding of what is the expected long-term value that we can expect starting from some state S. And this is the formula that we also had in the beginning. So we can actually, if we can actually approximate the long-term value of a state S given by this, we can just easily say, okay, let's just maximize this. So we actually want to just maximize the expected long-term value that we can have from a state S. Easily said, but actually, what does it mean to maximize the expected return E? How can we maximize this at all? Actually, we need a controller that helps us to select the actions that actually lead to larger returns. And a policy pie is actually what this controller looks like. So we talk a lot about policies in reinforcement learning because the policy is the main ingredient that selects the actions. And we actually wanna have this policy pie. So a policy pie determines the agent's behavior, so its way of acting. And basically a policy is a mapping from a state space S to an action space A. This means that it's equivalent to a function, so mapping S to A. Just to be complete, we see different types of policies in the following lectures. There's deterministic policies, which just returns. You just give the policy a state, and it will return an action that you should take to maximize your return. Or you have stochastic policies that actually define a probability distribution over actions. So actually, what does it mean if we want to maximize the expected return of our samples? This actually means what this actually means is we want to find a policy that gives us a state action mapping that maximizes the expected return. So this is actually what we will deal with in the next lesson. One final remark, a little bit towards terminology. I said it also in the previous lesson. There is the control community that deals with very, very similar problems for also a long time, but there is a slightly different notation on this. So we learned about states and actions and reward with S, A, and R. The control community uses X, U, and C, which basically is almost the same. So X is the state representation, U is the function, so the utility that you can do, and we define a cost function, which is basically similar to reward function, but it's still the opposite. There's also some nice wrap up from Berzekas again, which exactly says this. So we have the reward, the state, and the value with the cost, the state, cost, and the opposite of the cost function. In RL we talk about agents. In the controls, we use a decision maker or controller. In reinforcement learning we talk about actions. In control community it's the decision or control, and the environment in RL is the dynamic system in the control community. In the next lecture, we will learn methods to actually solve an MDP and actually to estimate a value function that lets us derive a policy that we can use to actually maximize the expected return we can get out of the environment.